In an earlier episode, we introduced the idea of harmonically related complex exponentials.
Yeah, I don't understand what their practical significance is. I mean, why do we need to consider harmonically related complex exponentials?
The reason is that they have some extremely useful properties. Let's dig deep to find out. What do you get when you integrate e power j omega t? Integration is usually interpreted as the area under the curve. But which area are we talking about in this case?
Euler's formula to the rescue.
Yeah. So we see that this integral can be calculated using the area under these two curves. We also see that this value is directly proportional to the difference of the complex exponential evaluated at the limits of the integration. So what happens when you integrate a complex exponential over its fundamental period?
Well, it's at the same position at these two instants of time, so 0?
Do you think it's always 0 no matter what omega is? When omega equals 0, we get t as the answer. Note that the fundamental period is undefined in this case, because the value of the complex exponential is the same at all times. So this equation holds good for any value of capital T. So in general, over t, we get 0 when we integrate a complex exponential with a non-zero frequency. Now, what can you say about integrating the product of harmonically related complex exponentials? Except when the two are complex conjugates, for all other values of n and m, we get 0. This is one crucial property of complex exponentials.
No offense, but I don't see what the big deal is.
Okay, let me explain. Whenever we think of representing a point on a 2D plane, usually such an image comes to mind. In fact, we can represent all the points even if the vectors were chosen this way. Any set of n vectors that can be used to reach every point in an n-D space is called a basis. Now, a basis of an n-dimensional space has exactly only n vectors. Although there are many sets of basis vectors, this is more intuitive because the coordinates of the point are the same as the coefficients used to reach the point with this basis. Well, that's obviously because we have chosen the two vectors to be along the x and the y axis. This makes one vector have no component along the other axis, with only 0 being common between the two. Such vectors are called orthogonal vectors. To know if two vectors are orthogonal to each other, we check if their inner product, or in this case, the dot product of the two vectors is 0. In other words, we check if the two vectors make a right angle. So these are a few examples of orthogonal bases in R2. The inner product of a vector with itself gives the square of the length of the vector. When two orthogonal vectors have unit length, we call them orthonormal vectors. These are a few orthonormal bases in R2. Now, in the complex plane, the inner product is given by this equation.
Why is the conjugate considered?
If you don't consider the conjugate, we won't get the length of the vector.
Oh.
This concept of orthogonality is not restricted to just 2 or 3D spaces. Although hard to visualize, it holds good for any n-D space.
For any n? Can n be infinite?
Yeah, why not?
Then v1 and v2 would have to be infinite dimensional vectors. That's weird. What would have infinite dimensions?
Now, a continuous time signal can be thought of as an infinite dimensional vector.
Oh, because it is defined over a continuum of values of time. Nice.
Exactly. Note that this signal could be real or complex. So we can extend the idea of orthogonality to an infinite dimensional space by replacing this summation with integration. Alright, let's get specific here. Let's consider an infinite dimensional space where each point corresponds to one period of a continuous time periodic signal.
Every vector in this space has a length, right? What is it about the signal that this length corresponds to?
Great question. So here, the length of a vector means the inner product of the signal with itself. So any signal which is square integrable is a point in this space. The area under the squared magnitude of a signal is called the energy of the signal, and that's the length we are talking about.
Oh,
Okay, so we are currently dealing with an infinite dimensional space where each point corresponds to one period of a continuous time periodic signal, and this has finite energy. Okay?
okay. But I kind of forgot why we started this discussion.
Yeah, I'm getting there. Hold on. Now, continuous time complex exponentials are square integrable functions, so they lie in this space. And this equation, whose significance we wanted to understand, says that harmonically related complex exponentials are orthogonal to each other. It turns out that they form an orthogonal basis in this infinite dimensional space. We could scale them to get an orthonormal basis as well.
Oh, so we can use this basis to construct any signal in this space.
Exactly.
That's really awesome. But how do you find these coefficients?
Suppose I want the kth coefficient alone. I can isolate it by eliminating the effect of e power j k omega t. How can we do this mathematically? By multiplying it with its conjugate. When we do that, we get this equation. Now I want only this term. What should we do? We can use the fact that we are dealing with a convenient orthogonal basis. So let's integrate on both sides over one time period and cancel all these terms, which leaves us with the kth coefficient. Now let's consider this periodic signal and shift it to get a new signal. How do you think AN is related to BN?
The two signals look pretty similar.
Note that this equation also includes a constant term to account for any shift in the amplitude.
Ah, nice. So here, only the constant term is different?
Yep. We saw how to calculate the ANs. Now to calculate A0, we have to cancel the effects of all these complex exponentials. This can be done by simply integrating both sides over a single time period. So the constant term can be calculated like this. This way of representing a periodic signal using a sum of infinitely many weighted harmonically related complex exponentials is called the Fourier series. Okay, that was a mouthful. Anyway, using this representation, we will see that the analysis and manipulations of a signal become much easier. Since a broad class of periodic signals can be represented this way, the Fourier series is a very powerful representation. Okay, let me leave you with a few questions. We saw that the harmonics of a complex exponential are orthogonal to each other. What about the harmonics of a sinusoid? Are they orthogonal? Let y of t be the sum of all the harmonically related complex exponentials. What do you think y of t looks like? I hope this video helped you appreciate the beauty of continuous time complex exponentials.
Beauty?
Go away. Anyway, we'll explore the Fourier series in more detail in the next episode. So stick around and we'll meet you in the next one.